We have a series of lectures about quantum error correction, and much like in quantum error correction, where the information is cleverly distributed amongst several qubits, the information in this lecture is distributed amongst two different lecturers. So we have Ben Krieger and Kieran Ryan Anderson, and so they'll be doing tag teaming, giving one lecture after the other. So I think we'll kick off with Ben here.
Yeah.
Thank you very much.
The company also doesn't let us travel on the same plane. Well, okay, so whenever I'm lecturing, I'm reminded of like being in kindergarten and talking to kids who are in kindergarten. No matter what you say to these people, they stick their hands up. They go, "Why? Right? Why are we learning this?" And the job of the education system, right, and the government is to beat that impulse out of the children. So they never ask why they're learning something. They just learn whatever it is you tell them to learn, and then they regurgitate that information at the end of the semester. But luckily, your experience, I hope, in government education institutions is now complete, so we can resume asking why. And we can do it right at the beginning of the lecture, so that you'll have an idea of where we're going, what we're trying to achieve. There's a double-edged sword, right, to quantum computing. These devices have exponentially large Hilbert spaces inside of them, which makes them really powerful, right? There's all kinds of stuff that you can do in that space, as long as you can design some clever measurement at the end, or turn your problem into a wave and apply a Fourier transform to it. But also, that exponentially large Hilbert space makes them really tough to analyze, right? Good luck trying even to find out what the effect of some unitary matrix is on a vector when you're dealing with 200 qubits or something, right? Even with arbitrarily large supercomputers, it's going to be really tough. And if you can't figure out what one gate does, good luck designing an algorithm, good luck understanding data structures, or any of the higher level abstract things that we want to do to create a real branch of computer science. However, not everything that you want to do with a quantum computer requires its full power. In error correction, me and this guy, we are spending our entire lives trying to figure out how to get a quantum computer to do nothing. And it's very easy to describe that operation. You can do with one symbol, right? And this thing is worth a lot of money because quantum computers can't do it. Well, they also can't do this, right? So you want to prepare zero state, you want to do nothing, you want to maybe measure in the X basis. None of these things are possible with fidelity 1. You always get some operation that's kind of close to the X measurement of the zero prep or the identity. And so given that the things that we want to describe are all really trivial until we compose them into big circuits, and we're going to have to add a lot of overhead, how do we come up with some theory of quantum mechanics that allows us to process non-trivial states, like highly entangled states, for example, in polynomial time, right? And today we're going to go over one way to get that done. And that way, people call it Gottesman-Knill after some of its authors. People would say stabilizer operations if they know about stabilizers. Most of the time, I would just say Pauli's and Clifford's. Although, given that this is professional rather than academic, we don't settle on terminology. We just sort of juggle different terms around, and if anybody gets confused, we leave them behind for the wolves. All right, so why Pauli's and Clifford's? There are many different efficient subtheories of quantum mechanics that you could focus on. Some people do tensor network states where there's a limited amount of entanglement. That's very good for condensed matter where things can be at weird angles in different bases, but the amount of entanglement is sort of area law limited. There's also fermionic linear optics or match gates. If you want to get a postdoc, get good at one of these subtheories. You can even design error correcting codes in these subtheories. But why would we do it with these, Pauli's and Clifford's? There's a few reasons. The first is versatility. A lot of the problems that you see in quantum computing, like finding the ground state energy of some Hamiltonian, you look up the Hamiltonian and you see it's a bunch of Pauli matrices. Some people in fault-tolerant quantum chemistry focus on a problem called qubitization, where they take some problem and turn it into a bunch of Pauli matrices, right? Given that they're doing all that work, maybe we can sort of live nice, easy, lazy lives by just focusing on Pauli matrices. And of course, anytime you see fermionic creation and annihilation operators, people would say, do the Jordan-Wigner transform. Now it's easy, right? It turns it into Pauli operators. And then there's quantum errors and error correction. We'll see later in the next lecture that if you can correct Pauli errors, then you can correct a lot of stuff. And yeah, nobody believes that they're going to get their physical error rates, down below 10 to the minus 5 without some kind of protection. Like even the topological qubit people are edging on error correction. They're doing like everything but error correction. And I think they would get down to 10 to the minus 6-ish. But if you want to run an algorithm with billions of gates in it, right, then you can't tolerate thousands of failures distributed somewhere in the circuit, because garbage in, garbage out, and everything's going to become a gigantic analog mess. And for this reason, we design codes using Pauli's and Clifford's in order to do a bunch of active error correction in firmware, basically, right? So it's a layer of the quantum stack. It's a term which I abhor, that goes between the hardware, and it sits just on top, so that what you provide to the user or to the higher level routine are virtual operations. Right. Pauli operators can be used to detect Pauli errors. We're going to see this in a minute. And there are these Clifford things that can be used to transform Paulis into other Paulis. And the machinery for moving errors onto ancillary apparatus that can detect them is all very neat and tidy. So yeah, basically ease of use is one of the main reasons for this. And all we're going to need to know to start is a little undergraduate quantum mechanics, or maybe first year masters, a little group theory, and then we can get going, really. Okay, so let's do quantum mechanics in like 15 minutes. Chapter 2, Nielsen and Chuang. If you're not reading Nielsen and Chuang, you're doing it Nielsen and wrong. All right. I should have started my lecture with a joke, right? Variational quantum eigensolvers. Okay. That was a good one, huh? All right. Pure beef. We can represent quantum states using vectors. This is a postulate of quantum mechanics, or like an axiom, which is a fancy word for something I will say without knowing how to prove. And that, looks kind of like some normalized weight 2 vector, no big deal. There are operations as well, which are usually unitary, inshallah. You could have, for example, something like so, 1, square root of 3 minus the square root of 3 and another 1. You could apply such a unitary to such an operation, and it only really gets complicated when you start dealing with measurements. Okay, so let's deal with measurements now. These are going to be operators which are observables, called O, that will decompose, right there. I think everybody's familiar, like, these are Hermitian matrices. They have real eigenvalues. You can diagonalize them. Anybody who's not, familiar with this should like pull the parachute right now and get sucked out of the lecture, because you might get lost later. Although it's okay. You're young. You can sit around and be lost for an hour. It's fine. But you would decompose one of these into so real valued eigenvalue, and then these projectors pi j. And when you perform a measurement, here is what happens according to the postulates of quantum mechanics. You would receive an outcome lambda j. Sometimes multiple lambda j's are identical, and so you won't know which j corresponds to which lambda j. So you can project into a subspace rather than projecting into a state. But you get out these lambda j's, and you get one out with probability pj equals whatever your initial state psi was that you're doing the measurement on, projector psi. So basically, this is like an inner product between a rank 1 projector psi and this projector here. So you can think of it as like how much of this state is in this space, basically, because it defines a norm. And then psi gets mapped to, right, under the action of this projective measurement, when you discover that it was lambda j, you get pi j psi, right, which is just the projection of this state into this space divided by square root of pj. And all this term does here is normalize the state again. So this is like conditional. If you were assured that the measurement had occurred but not told the outcome, you would get a mixture of these things. And it would be a convex combination with scaleless pj. All right. We are not going to use the Heisenberg picture, but I have to tell you about the Heisenberg picture anyway. All will be revealed. No worries. Let's imagine like a really complicated experiment in which some state is prepared, it's then exposed to some unitary evolution, and then we measure out some observable. Can everybody read my handwriting, by the way? Even people in the back are nodding. Okay, we're good. Right. So what's going to happen? The only things that we observe are these eigenvalues that come out of the end here, right? These little lambda j's. And they each show up with a pj, where I have to stick in the evolved state now. So I'll conjugate the evolved state, psi u dagger, right? Pi j, u psi. And then the projection takes u of psi. Right, this thing maps to I, j, u, psi over square root of pj. And I can just rub this thing out and stick the dagger on there. And now we see what happens to the initial state. It goes to u dagger pi j u psi. Okay, so two things could have happened. It may be that psi evolved to u of psi and then got measured, or it may be that the projectors, right, and therefore the operator itself, sort of evolved backwards, right, under this u dagger pi j u, and then was measured against psi. And because the outcomes of physical experiments that obey the laws of physics don't distinguish between these two cases, they're like equivalent. And so you can use operator evolution in order to say what has happened in some physical scenario rather than having to evolve vectors. We're going to see an instance of this again, although it's not quite the same as the Heisenberg picture. Although the paper that this comes from is called Quantum Computing in the Heisenberg Picture or something. At any rate, we're going to start evolving operators in a minute. Apologies to the Masters in HPC program. You should all go get a Masters in HPC, but I need Blackboard space. So it's going down. HPC, criminally underrated topic, though. Right. So now that we've covered quantum mechanics in 15 minutes, let's do like 10 minutes of group theory. This is what it's like being in quantum computing. You wake up and you come to work not knowing whether it's going to be algebraic number theory, atomic physics, this stuff, and you just sort of take whatever the day has to offer. So if, if you're kind of good at a lot of different types of math, apply for a job or something. All right. Now, again, I'm not a mathematician, so I'm going to start with the punchline. Group theory is a way to cheat at matrix multiplication. Using group theory, you don't have to write out all of the elements of the matrix in order to calculate matrix products. You can just look it up in a table. And often, or for big enough matrices, that can mean you take polynomial time or like linear time even, so like a professional's polynomial, not like n to the 10 or something, rather than doing exponential time. But a mathematician would say, you know, a group is a set endowed with an operation, et cetera, et cetera. And well, okay, we have to do that now. So a group is a set endowed with an operation. There are, you know, there's some set G with little elements G, and there's an operation which will take two elements of G and give you a third element. And typically you write it with a little circle or you don't write it at all. So I would say something like, you know, G prime, G double prime equals G triple prime, right? And you can think about it like multiplication, even though for some groups it acts more like addition. And the point of group theory, right, is that you're abstracting away which mathematical operation it is. You're just talking about its properties. Right, so every group that I times G equals G times I equals G for all G in the group. And you have to have an inverse G inverse such that G inverse G is G, G inverse is identity. Okay. Group theory has a ton of applications. There are a lot of different groups. You can do like Rubik's Cubes with group theory. You can do robot arms. You can do cryptography. You can do whatever you want. But we're going to look at a group with 4-ish elements, which is just some Pauli matrices. Okay, so our identity is going to be this 2x2 identity matrix. We're going to have X, Y, and Z. We've already seen these matrices pop up a ton of times, so the fact that we will no longer have to multiply them at the end of the lecture, right, is going to be very advantageous. Anytime you see one, you'll be able to start thinking about it, in linear time rather than trying to remember where the minus I goes, for example. Don't worry, that one's correct. And we will see that these things form a group because they're closed-ish under multiplication. So for example, xy is equal to You'll see look at how tedious this is, right? I already know the answer, but I can barely I'm writing so much. You can always define the group operation that you're going to use to be multiplication where I delete the I afterwards. That's fully mathematically legitimate, right? It provides a map from two elements of the group to a third. It's a group operation. Deal with it. And then, let's see, we can do a whole table. I forget what these tables are called, but you can make a whole table of, let me do, the little circle means I'm deleting the phase, yeah? So I can take I, X, Y, Z, I, X, Y, Z. And I get identity, 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 identity. X, Y, Z. And then this thing is going to be, well, Z, Y, Z, X, Y, X. So now I no longer have to multiply these matrices whenever I see them, right? If I've done the work once of showing that this is closed under multiplication, then there's only a finite number of things that it can be, and I can look them all up in this table. Which, yeah, okay, I can see that you're not rolling in the aisles, yelling hallelujah yet. It's not very impressive that I know how to get rid of 2x2 matrix multiplication. But don't worry, the next page, these notes go on. So we will also be able to do this for tensor products of Pauli matrices. Oh, I left the cloth over here. I don't even need it, actually. Let's just make another weird, ugly line, do tensor products. Did I already say that I would make these notes available? So if you want to write things down, you can, but everything I'm saying is roughly in here. So writing is optional if you're just not that kind of person. Okay, so a tensor product is how you describe mathematically operations that occur in parallel, and it's easiest to see what the properties of a tensor product are if you do it diagrammatically, right? So I'm going to use this funny symbol. So who's seen the O times before? LaTeX O times? Oh, most people, fantastic. Callum saw it, yeah, very useful that you've seen. It's the target audience, guys I work with. Keep your hand down. So A tensor B is represented by, right, A, B. So it's when I have a composite system, it's got two subsystems in it. I do the operation A to one and B to another. And you can see really easily one of the properties of the tensor product, which is how it composes with the series product. And it's so important that I got to write it high up, but then I'm leaving real estate. Who cares? All right, so A, O times B, C, O times what these things are called. It'll be correct in your notes. Okay. So if I join these wires together, we can see, right, just by sort of changing the bracketing, right? This is AO times B, CO times D. But if I instead, if a tensor product wore pants, would it wear them like this or like this, right? If I instead do this, you can see that this is equal to AC times BD, where time runs in the opposite direction or whatever. But it doesn't matter, because the names are consistent from here to here. And this is a very valuable property because it allows us to, right, anytime I can multiply 2 by 2 Pauli matrices and get the answer just from table lookup, I can do that here, and if I had a longer tensor product, I could do the same thing. And it would just be a linear number of steps rather than some exponentially big matrix. Super convenient. I'm going to go all the way over here to introduce a very tightly related property because I'm out of board. But that's also okay. Form of pro tips. If you have eigenvectors and you take a tensor product, right, so it's A tensor B, and then I feed that into the operation here, then I get the product of the eigenvectors AB. So anytime, oh yeah, and by the way, people often write tensor products just inside the ket, just a big list of symbols. And that way you can do stuff like, it's just a sub everything, right? Your theory of quantum mechanics includes a set of states, a set of operations, and a set of measurements. So we're going to take a subset of the states, a subset of the operations, and a subset of the measurements. And, well, okay, you could, any old time you do that, that's a subtheory. But is it efficient? Well, if you can describe all this stuff that I'm erasing right now using a polynomial amount of space and time, then it's efficient. And we will see how to do all these things. You can go read about this if you want to. So let me recommend some reading over here. Daniel Gottesman's PhD thesis. It's from 1997, but it's still like the most up-to-date reference on like the basic theory. Oh, let's see. 5052. Yeah, and if any of you have to write a PhD thesis soon, that's more or less how it's done. And you can also go read Aronson Gottesman 04. Actually, if you just go to Daniel Gottesman's website at Perimeter, there's like a big list of everything that you should read instead of listening to me. But I won't tell you where that is right now. You can learn later. Focus for the time being. All right, so if a Pauli is a matrix, how do I describe a state using that matrix? Aren't states vectors? Sure. But I'll just say that the states that we're going to use are going to be a +1 eigenstate of some Pauli operator. And if I do this for 1 qubit, right, then x times the plus state that we saw earlier is equal to plus. And for y, there's something like plus I or I plus, which is equal to 1/√2 1i. Let me make sure that the dot, okay? And then z is maybe the easiest to describe because that's the 0 state, right? 1, 0. And if I want over √2. And likewise, I could put a minus sign here or here. If I put the minus sign on the z, I get the 1 state, which when you multiply by the z, you just pick up that 180-degree phase. So this works perfectly for single Pauli matrices. Let's do it for tensor products. What we notice is if you take x tensor x on plus tensor plus, right, then you get plus plus, no problem, but x acting on minus minus, notation is getting continually more compact, is going to be equal to minus 1 squared, times minus minus, which is just equal to minus minus. So if I have a single Pauli that acts on multiple qubits, it doesn't specify a state on its own, it specifies a subspace. How do I say that we should solve that problem in the notes? First, we should talk about how big this subspace is. If you want to keep specifying states that are in that subspace, maybe get it down to 1 state, hopefully, then you got to know how big these subspaces are. All right, here's where it gets a little bit tricky. I'm going to denote the set of eigenvalues of an n-qubit Pauli, lambda n, for a minute. Every one of these Pauli matrices has a +1 eigenvalue and a -1 eigenvalue, 2 +1 eigenvalues, and like minus identity, which has 2 -1 eigenvalues. But I can divide this. So if I picture this as being a giant tensor product, and I know that the eigenvalues are scalar products, I can pop the first term off the tensor product and say that this set union with lambda for every lambda, in lambda n minus 1. And if you try a bunch of examples, you will quickly become satisfied that each one of these sets, for every time there's a +1, there's a -1, and vice versa. And so each one of these sets is just going to be half +1s and half -1s, unless you do all identities or all minus identity, right? Right. The all identity operator will have all +1 eigenvalues, and then minus identity will have all -1 eigenvalues. So each one of these operators cuts the space in half, right? So now with your little CS brains fully active, filled with potato salad and caffeinated, you're thinking, aha, I'm going to use a logarithmic number of Paulis, right? Each one cuts the space in half. So in order to go from 2 to the n down to some constant, I only need something like n of them, rather than 2 to the n, which is what the number of coefficients I would need in order to write out the ket. And you would be right, because you are a fictional version of yourself that lives only in my lecture notes. All right, so when, right, so this Pauli acts on the state like so, we say it stabilizes the state, and let me erase some more stuff. Look at me checking the time like I'm not just going to go until I run out of notes. Anytime you've got two operators that are both stabilizers, we'll call them S, J, and SK, right? And it's going to act on some psi. If psi is stabilized by SK, this is equal to Sj times psi. And if this operator is also, if this vector is also stabilized by Sj, this is equal to psi. So any state that's stabilized by these operators individually is also stabilized by the product, right? So we don't have to keep track of every possible Pauli that could be stabilizing our vector. Most of them, which means all their elements commute, right? And the reason that no anti-commuting Paulis are allowed is because with this product relation, if we had two Paulis in here that anti-commute, if S, J, SK, minus SK, SJ, I could start taking products like SJ, SK, SJ, SK, switch these two, and I get minus Sj squared, SK squared. The product of every tensor product of Pauli matrices with itself is all identity. You can see on the diagonal of this table. So this is equal to minus identity, which, as we said, does not have any +1 eigenstates. So it can't stabilize anything. Right, so anti-commuting Pauli's in reduces to your stabilizer space is 0-dimensional, go home. So no anti-commuting Pauli's allowed. And if you're going to write down a generating set, they should all be independent under multiplication. We will see quantum error correcting codes in which they are not. And there are reasons why you would measure those that are redundant, right? Just in case there's a measurement error, you might want to say, oh, I have multiple different ways to reconstruct my generating set so I can see whether they're all consistent. But if you want to accurately describe Sj and Sk, already stabilize the state in question. Perfect. So that's how you describe states. It takes about n² bits of memory, depending on how many bits per letter you use. And let's see. It's the 18th of April, very useful information. It's also about 2:06. I think we can afford one example before we move on. Who can tell me a legit non-trivial Pauli that stabilizes the state? I joke around, you don't get to joke around. My bag is secure, your career hinges on this. ZZ? Okay. So we multiply ZZ on 0, 0, +1 squared, or -1 squared. Right. That stabilizes the state, very good. Do we need any more? Or is ZZ the only stabilizer of this state? YY. Someone came to play today, but I'm not going to put YY, I'll put XX. Why am I allowed to do XX instead of YY? Yeah, because when you multiply them, you just generate whatever you want. And you'll notice that I've ignored the I, because there would be two i's that make a -1. Right, so if you flip, you get 1, 1 here and 0, 0 here, and then the addition is commutative, and that gets you back your original state. All right, good. People are roughly getting it. Fantastic. So now we're done describing the states of our efficient subtheory. Let's start going from state to state with unitary operations. So we will consider U acting on psi. We might pray that, there will be some other stabilizer that stabilizes this state. And I'm going to guess that there is, and then there is, right? So let's guess that there's some Sj prime that stabilizes U of psi. Right. That means that Sj psi, by hypothesis, is equal to U of psi. However, we know psi is stabilized by something, so we can stick a stabilizer in here. Common proof technique. We can also stick an identity in here when I was doing the Heisenberg picture, because these operators are evolving forward in time. So it's a Heisenberg-ish picture. Right. Also, do these stabilizers commute? Do they generate a group? Let's prove that they do. Why not? Let's do generation first. So U, Sj, U dagger times U, Sk, U dagger. Everyone can already see where I'm going with this. U dagger U is eliminated, and this is equal to U, Sj, Sk, U dagger. So anytime I take the product of conjugated stabilizers, that's the same as if I conjugated the product of the stabilizers. So, this is a stabilizer of the new state because the product was a stabilizer of the old state. So I'm taking the products of stabilizers, I still get stabilizers. My new operators form a group just as my old operators did. And, because products are preserved, group commutators are preserved because those are just fancy products. So it's abelian still. Fantastic. But maybe not necessary condition that I will nevertheless use today is that these operators, U, S, U dagger, also have to be Pauli operators. So all right. We've got the group homomorphism property, mathematicians, I said homomorphism, that you will want to know about in your life. At least if you're here. I mean, you don't need to tell your family over the holidays or whatever, unless they're also involved. But let's get in. So, name, diagram, unitary matrix. Just one last time, I'm going to write out unitary matrices. And then we're done with unitaries. And so Pauli's, oh yeah, okay. One of the things that you would need to say about Clifford's is that, okay, maybe I shouldn't give you these notes, but I should update them first. Because of this property here, whenever I take whenever I want to calculate the effect on a product, I can just calculate the effect on individual generators and then take the product afterwards. That means that in order to specify a Clifford fully, I don't need to know all 4 to the n possible things that may happen if I stick some arbitrary Pauli in. I only need to know the effect of the Clifford on a set of Paulis that generate the Pauli group under multiplication. And that generating property gets us down from an exponential number of Paulis to a linear number of generators. So when I complete these tables, now you will understand why they are complete. Okay. Pauli maps. So C naught is a Clifford. Some people put an X here. I usually put the bullseye thing. Notation is not consistent, and if you don't like it, tough. Unitary matrices are consistent though, right? So in the 0 sector, right? We have the identity. In the one sector, we have this x. It's a controlled x operation. But we quit writing these things, and we begin writing these things. So x tensor identity maps to classically as being if this, then do that, propagates information, right, in this basis from target up to control. And this is the reason why if you surround a C0 with Hadamards, you get a C0 running in the opposite direction, which shows up a little more visibly in these Pauli tables. Now, speaking of Hadamard, Hadamard is also a Clifford. Luckily, notation for this one is fairly consistent. Last time I'm going to write that unitary matrix. Fantastic. And this one takes x to z and z to x. And it takes y to minus y. You may or may not need to use that minus sign. Watch yourself. And then finally, there's a gate which has no fixed name. Some people would say P. You can say R. Right. In this set of notes, I've called it S. And it is, well, OK, you can think of it as the square root of Pauli z. Pauli z sometimes also comes with a factor of 2. So you always have to watch yourself. You write it as an S or a P or an R. Write 1, I, 0, 0 is this unitary matrix. And this one takes x to y and z to itself. These three gates, as you compose them, can generate any Clifford. Will I prove this? No. It would take too long. But let's do a pretty involved example. I have 15 minutes left, and we still have to do measurements. I'm going to run long right now. But that's OK. Everyone's having fun. I've stayed focused. I haven't goofed around. So let's prepare an entangled state. X, 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 X. I'm just going to write in a big table to try and find a Clifford that does this. There is an algorithm for doing this. Will I tell you what the algorithm is? No. I'm going to do what you're going to do when you start working with Paulis and Cliffords and just try some stuff. So I know, for example, that there's entanglement in here that I'd like to break, right? And you can tell when one of these states is entangled because it has, weight greater than 1 stabilizers that intersect each other. If ever you see one of these tables that's block diagonal, like there's some stabilizers up here and some stabilizers down here, but then identities in the off diagonal, then you're dealing with 2 unentangled blocks. Maybe you can prove this to yourself. We don't have a ton of time. All right, but let's take a look at what would happen if I ran a C0 between qubits 1 and 2 of this state. So in order to figure out what happens to XX, I multiply the outputs of these two, right? So XX times IX is XI, right? So my XXXX goes to XIX. Let me say what's going on here. C0, 1, 2. ZZII. So in order to, well, let me be real fancy. C0 is self-inverse. C0 times C0 is the identity, which means if I read this table backwards, it's legit. ZZ goes to IZ. So IZII. Nothing happens to this Z, or does it? No, it goes to Z, 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 I, and I, Z, Z. Yeah, stabilizers in order to generate a new generating set. So I'm going to multiply this by that in order to put an identity here. And now I can see that I have, a 1-by-1 block, right, where I have identities in that row and that column. So this qubit is separated out. So I can derive, and you can run this circuit forwards for yourself, that if I do this, what I get out is this stabilizer state that I wanted. I encourage you all to try this as an exercise in order to keep up. I mean, not like right now, but snap a picture or take a note or whatever it is you do. And that also turns out to be a pretty important state in quantum error correction. That's called a cat state, because it's a superposition of 2 macroscopically different bit strings. Right, so now that we've seen a Clifford circuit, I'm immediately going to start using them as an abstract proof technique, because we're going from like 0 to 100 today. Oh, we started a few minutes late. I get extra time. No one can stop me. Right. Let's imagine, won't you? Let's imagine a cloth that I can use to wipe down the board. It's just like dealing with my kitchen. I have a 5-meter long table, and the thing I need is always the other end. Let's imagine that, just like that last circuit, which is all the way over there, we've got some abstract Clifford C that we're going to use to prepare a stabilizer state. And at the input, we're going to put a bunch of weight 1 Z stabilizers. Right? These are like little 0 states, and we're going to prepare a big ket over here. What if I was to leave out a few of these? Well, then there's a whole set of stabilizer states that we could be describing. If we put a Z in here, that would be one state map, right, to produce logical qubits at the output, right, whose operators are like the stabilizers that would happen if I put a Z or an X in here, right? Those become your logical operators. And they have the same commutation relations as the Paulis, because they're unitary equivalent to the Paulis. And so they act just like Pauli operators, but on logical qubits. I'm looking at the wrong set of lecture notes. Right. Fantastic. So when you want to do a table or tableau, a lot of people say tableau. You have to, it's not enough. If we said table, it would be too English and low class. You got to have a tableau. So let's talk about one of my favorite codes. We will have 2 stabilizers. Called SX and SZ, Z. And then we'll have some logical operators. X bar, the bar denotes a logical operator. X bar 2, and Z bar 2. This thing is going to be X, X, I, Z, I, Z. X, I, X with the other 2, for example. And any one of these logical X's or logical Z's, it has the appropriate commutation relation with its other powers. The hardest part of dealing with the stabilizer subtheory. Luckily, we already detailed that any tensor product of Pauli matrices has +1 eigenvalues, -1 eigenvalues, and that's it. And that means you can describe the set of projectors as identity plus P over 2 minus identity minus P over 2. Each one of these things, this is going to be like pi plus and pi minus. Those are the only 2 outcomes you can get from a measurement. And when you do a measurement on a stabilizer space, what happens depends on the commutation relations between the new Pauli that you're measuring in and the existing stabilizers. Let's do the easiest case first. If the Pauli is in the stabilizer group, then the probability of getting plus, right, is just psi I plus P over 2 psi. But we just said, okay, so stabilizer. P is a stabilizer, right? So P psi equals psi. Identity of psi equals psi. So this is just equal to 1. So this is just equal to 1/2, psi plus psi plus psi, right? 1 plus 1 is 2, so the probability of getting the +1 outcome is 1. And it should come as no surprise to you that when you project a stabilized state onto one of the stabilizers, you just get that state back, right? It acts as the identity, both as a measurement and when you apply the operator. I think even in software that I've written, I would just skip measurements sometimes, if I can. All right, so we don't know what the probability is a priori, right? Because P here is some new operator. Psi can be some arbitrary superposition of eigenstates of these operators. It doesn't have to be +1 or -1 with respect to any of them. But we can talk about the output state. So our output, psi, is going to map to identity plus or minus p over 2 times psi. Square root of pj. Sure, it's normalized. Why not? S times I plus or minus p. Here we get lucky. S commutes with I, S commutes with p, and so it commutes with I plus p. I can move it through here. S stabilizes psi, and so psi maps to a state that is still stabilized by every S in the stabilizer, right? However, there's a new operator in town. Well, okay, there's almost a new operator in town. If I put P here, right, then P, okay, I plus P is equal to P plus I. Yeah, is equal to I plus P. But P times I minus P. P squared is equal to the identity, right? So this is P version of that Pauli is going to join the stabilizer group, right? You're projecting the state space down into a state that's half the size by adding a new constraint onto the state. Right, and now, the final boss of the lecture. It looks like there's 2 pages, but there's just concluding remarks on this last page. If the Pauli we're measuring anti-commutes with a stabilizer, then we're going to get to see some more of these commutation relations. All right, so first off, let's say there's some old stabilizer that anti-commutes with the measured operator. I plus or minus P over 2 square root of P. Okay. Some probability. Okay. This is going to be equal to 1 minus a plus P, 2 root P, psi. Right, this plus minus has become a minus plus, so it's not stabilized. And, let me see, it's Sj. So there's going to be, if you're anti-commuting with at least one stabilizer, then one stabilizer that you anti-commute with, at least one, does not stabilize the state anymore. It's removed from the table. But let's take the product, Sj, Sk, of 2 stabilizers that we will assume anti-commute the fresh state identity plus or minus P acting on psi is stabilized by the product of any 2 stabilizers that anti-commute. So in order to figure out the new stabilizer generators, you make a list of everything that anti-commutes. You pick one, your choice, because it's the same as multiplying the stabilizers to generate a new group. You blame that stabilizer for all of the anti-commutation, multiply the remaining stabilizers with it until you get the biggest possible set of commuting generators. That set of commuting generators and the measured operator become your new stabilizer, and the single whipping boy stabilizer leaves the table. Has to go to the kids table. Now with that, we can, all right, do we have just enough time? I think we have just enough time to do one last circuit simulation. So we're going to put it all together and do a 5-qubit algorithm in just a few minutes where, no offense to Catherine, but I think if we had tried to do a 5-qubit circuits in the first lecture, we would not have had a good time. 32 by 32 unitary matrices, we would have run out of boards. All right, so let's do a circuit that Kieran and I both care deeply about. muscle memory at this point, how often I write this thing down. I put a 0 state in. I do a Z measurement at the end. Z. Right, so my initial stabilizer tableau is going to have one stabilizer and then 4 logical qubits. So I'm going to have I, Z, X, I, Z, I, X, I, Z. Did I leave enough space here to X tensor X, right? Likewise, this X is going to map to XX, this X is going to map to XX, this one is going to map to XX. And the Z, let's see, these Zs, nothing is going to happen to them because they commute past the dot no problem. The only Z that gets changed by this is the initial Z here, right? This Z stabilizer is going to become a product of Z stabilizers on these 4 qubits and this guy at the output. So I'll put, maps under C naughts to, I've got the corner of the board here, so I'll leave a little awkward space, Z, 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 as my one stabilizer. X, I, X, Z, I, X, Z, X, Z, X, Z, X, X, X. Right, and that's it. Everything else is an identity. Yep. These columns line up, yeah, do they make sense? Yeah, great. Now I'm going to measure that Z at the end. That operator commutes with the one stabilizer that I have, so it's just going to join the table as a stabilizer. I'm also going to assume that I got the +1 outcome. It is going to any-commute with these logical operators. Oh no, I didn't cover that case. What happens if it any-commutes with a logical operator? Well, you should remember is that from all the way back over here with this big Clifford that I'm using to prepare states, a logical operator is just sort of a stabilizer in waiting. So I do the same thing, right? I multiply the logical group in order to find stuff that commutes with the group, and then I'm going to turn this into like XX, I. X, I, X, I, Z, I, X, I, X, I. Right. This group is also generated by, okay. Right, so we'll notice that there are no logical operators affecting the 5th qubit, right? There's one stabilizer affecting it, right? I can remultiply to do this. So this state is now separable. And what this means is, I now have, right, I've carried out through this circuit a measurement, a projective measurement of this wait for operator, and I've added and removed 1 qubit in so doing. And these are just the remaining, 3 logical qubits that satisfy that primitive stabilizer code. Still distance 1, right? You still have a bad time if you tried to use this in real life because, you only have to do 1 Z in order to mess your qubit up. All right. And that is it. Now you know how to do everything that we do on a daily basis. Commuting Pauli's through Cliffords, looking at the effects of circuits. Well, okay. We also let us know if you're interested. And with that, I think Kieran can take it from there and introduce the kind of things we're actually interested in.
Are there?
I heard all that stuff they were getting Glen with, like write bigger, write bigger. You gotta write bigger.
For 5 minutes to change the video at some point.
Yeah.
You gotta break it, or you want me to tell them to wait a bit? Maybe better if they don't interrupt you.
Yeah, wait, what?
When do you expect that you will your first hour? Well, I don't know. I do think that it'll actually, I have plenty of room to play with. So they're gonna keep on recording or something? Like, I thought they were going to like reset it. I don't know. This is the current schedule. Well, it's up there.
Yeah, so what happens is that the team doing the recording is available after some time. I don't remember if it's half three or something. And so they want to, so yeah, half three. They want to just change camera to an automatic one. It's going to decrease slightly the quality of the video, but that's just something that I can ask them now actually. I don't know how the team performs, so I would ask one of the.
Yeah, so actually Alexandre said. Team and he said, so I'm a tutor, but I don't know what was
Sure. I think I'm a mentor in Hackathon, so I'm not allowed to join the team. I can be assigned to their team to like.
That's just carrying stuff. You know, I mean, Ben said it's one of
Yeah.
the audience, but he's allowed to join the team as a tutor. Yes.
I think so. Well, I'm not sure. I don't know how it works. So, it's dependent on the use case.
Okay. So yes,
That's my understanding, but I would confirm that with one of the
okay,
organizers.
so I will ask Alexandre if
To sort of internalize this and understand.
This is pretty funny. I didn't think about we can totally imagine. It's just like very if someone walked in without any context. Yeah, no, of course. No, but every time I see it, I snicker. You know, because of all the quantum people. If they ever learned that we have a technical term called magic states, such, they would totally go in on that. Yeah. Think about that as being a joke.
I don't know if this is much better than my matrices. Just kidding.
It's all easy, but
Just kidding.
yeah, for time, sure.
5 by 5. Yeah.
So Oh, it's right there. Testing, testing. Yeah, so it's basically the number of qubits. So
Always the number of
0,
qubits.
1, 2, 3, 4.
All right.
Oh, well, okay, 1, 2, 3, 4. Like, sorry, from 0, but 1, 2, 3, 4.
So the first row is like the logical. Or is there anything distinguished with the first row?
So usually we put this, just the stabilizers plus maybe a logical, like just the logical operators, but he was kind of like keeping it fairly generic. I'll go over this again, in a simpler manner, or a different manner. It's cool. So hopefully it'll become more apparent. Yeah. 350. Well, so that'll be, hopefully at the beginning of Ben's lecture.
So you're lecturing for less than an hour.
Wait,
It's already
350.
48.
Yeah, it's fine. It should be fine, I think. Testing, testing. Guess it sounds okay.
Ready?
Sure.
All right.
Testing.
All right, welcome back. We're ready to kick off lecture 2.
Testing, testing. Oh, testing, testing. Now it works. Okay,
Good.
cool.
All right, thanks, Kieran.
All right, yeah. So I'm Kieran Ryan Anderson. I'm over on the US side of things. That was formerly Honeywell Quantum Solutions. So now I'll be talking about, hopefully it didn't scare you off with all the mathematics, but I'll be talking about the basics of QEC. So we kind of reorganized the schedule a little bit. So it'll be him, he just gave a talk, and then it'll be me, then him, then me again. I'll have a lot of pictures, so of like transistors. It's not at the scale where, for the most part, you have to deal with quantum error correction. To some degree, you have to deal with your SSS or SSD hard drives as well as DRAM memory. They're kind of, if the cells go out or the DRAM's kind of sensitive now, everything's getting squashed down, they have to deal with error correction. But generally, you don't have to worry about it for everyday consumer stuff. However, for data centers, you start to have thousands or tens of thousands of processors. So that's where it starts to become important. It's common for servers to have their RAM using ECC RAM, or error-corrected code memory. So even common servers have error correction in them. And the main sources of error for classical systems is cosmic rays or decay from particles in the packaging of them. Actually, I think Los Alamos noticed an issue where like they had these high-performance computers and they had a weird amount of error, and it turned out because they were like a mile above sea level that actually being closer, having a thinner atmosphere was actually increasing the error rate. And as we approach, exascale quantum computing for high-performance computers, this becomes really important. They have to start worrying about, or not quantum computers, classical computers. They have to start worrying about how to deal with errors due to cosmic rays. As we know, qubits are really fragile. Interesting to compare what their error rates are compared to their classical counterparts. So back in the day with the ENIAC machine in 1946, where it was one of the first sort of actually programmable electronic computers, they actually experienced, if you can do the calculation, for transistors. So that's pretty impressive. That's why your cell phones and laptops, for the most part, don't have to deal with error correction. Sometimes you get a blue screen of death, and that's actually from a cosmic ray. Not always, especially on Windows. But quantum technology nowadays is at 1 fault per 10 to the 3, 10 to the 3 operations, or 1,000 operations. That's significantly worse than vacuum tubes, and that's kind of sad. Although, luckily, these aren't directly comparable because we know that certain algorithms, we hope, have an exponential speed up compared to classical algorithms. So they're not completely comparable because one's far more powerful for certain algorithms compared to the others. But yeah, eventually, we're kind of living in the NISQ era, as people like to say, this noisy intermediate scale quantum computing. But eventually, we want to tackle these what are currently non-tractable difficult problems. So for example, breaking Shor's algorithm, or breaking RSA using Shor's algorithm. You might need roughly 10 to the 12 CNOTs in order to do that. So that means you need roughly an error rate of less than 10 to the minus 12. Those are really small numbers, and that's kind of hard to get. Even like in hardware, there's physics. So you need something else. And the main consensus is that we need quantum error correction. So as been mentioned before, quantum error correction is all about kind of spreading the information across multiple qubits, or qubits if you get fancy. Action of it is just doing quantum error correction. It's doing fancy identities, as Ben mentioned. Yeah, so you imagine that the user will supply some algorithm to our quantum device, which might be a hybrid system. Maybe it's a coprocessor for some high-performance computer. But in general, this gets sent down, and quantum error correction will do its magic under the hood. And there's a variety of things that it needs to do that you might not be familiar yet with. Potentially like magic state factories, these Clifford and Pauli operations on the logical level, like Ben mentioned. Logical memory, and so forth. But 90% of it, 99% of it is quantum error correction. So quantum error correction, as I mentioned, it's about encoding information over multiple qubits. And basically the name of the game is to, once you have this system that you're encoded, you're using the qubits as kind of a substrate for this other system that's built on top of it. And because you're building a system on top of another system, what you can do then is play a game where you can start trying to detect these faults and trying to mitigate it faster than they can corrupt your higher level system, your logical system. And that's the main idea of quantum error correction. It's effective. And now the screen went black, and that's fun. And now it's back, so experienced an error. Luckily, the system recovered. Also, technically, faults are about the lower abstraction level, the lower system, while errors are about what the user kind of sees, so on the logical level. So often, though, even in the quantum error correction community, those words are kind of used interchangeably. But yeah, errors are technically, a fault can cause an error, but it doesn't necessarily need to. It could be a benign fault. So for example, over here we see, if your game's freaking out, the user's seeing something going wrong, some bad behavior on the higher level, your logical level of the system. All right, some of you might be familiar with some basics of quantum error correction, some of you might not. So I'm going to do the boring thing and go through the repetition code. But it teaches you a lot about how quantum error correction works, and is very simple. So it's kind of a good example. So the repetition code is really a classical code. We can apply it to our quantum systems. But on the classical level, you really just have to worry about bit flips. So changing between 0 and 1 by, for example, cosmic rays. Often you kind of think of your bits going through some error channel that might have some problem. The whole name of the game, both in classical and in quantum error correction, is redundancy. So a very naive and simple way to protect your information is just to repeat your message. So this is called encoding, or where we take our original message and we encode it into a larger system. So we, for example, on the classical side, like we have a bit flip happening on the first bit, it flips it, but then we use a scheme called, for our decoding process, so the opposite of encoding. So decoding is trying to extract the message that we originally intended to give. We use, for the most part, majority vote for this repetition code. So what's the majority of this 3-bit message? It's 0. And so you'll be protected against any one fault, or bit flip fault. And you can see here, once again, a single bit happens, a bit flip happens on any of the qubits, you get back the original message, and that's great. However, if 2-bit flips happen, that's not so great. Then the majority voting scheme will tell us the opposite message. So we'll get back 1, for example, if with this first example. So 0 goes to 1, 1, 0, and the majority vote says that the outcome should be 1, and that's not right. So we're not completely protected. We're only protected to a certain amount of faults. But effectively, what we're doing is we're taking a channel that had a probability of p errors and changing it to p squared. So we're suppressing the noise by this bit flip code. And then, of course, we can just, if that's not enough and the error rates are high, then we can just make the message, that we can suffer 2 faults and still recover the message, because the 3 other bits are the majority, and their vote is stronger than the dissenting 2-bit flips, and so on. And in general, this length, the number of bit flips needed to change you from one message to another, is known as the distance. And that's used in quantum error correction as well. It's an important concept that is just a little bit lower than half. So d minus 1 over 2 floored. So you can apply this equation, you'd get 1, 2, and 3 from those previous examples. That's what t is. Yeah. And then in general, for the repetition code, the distance is the number of bits you have, but that's not true of general codes, even other classical codes. And then we can see if we were to keep on taking this scheme out to infinity, which is not something that you would do, then we could suffer, up to, not exactly, but up to half of our bits flipping, and we'd still be able to recover. As long as we have a little bit more than half that didn't flip, then the majority wins, and we get the message back. So this is this is basically what's known as a threshold. It's how does the code perform, a family of codes perform as you increase the parameter d out to infinity. And therefore you know that as long as the physical error rate is lower than that threshold, there's some large code in the family that can arbitrarily suppress the noise. Okay, so in quantum computing, often what we do is we kind of basically steal ideas from classical computing or classical information theory. And that's what we're going to do now. However, I didn't do the qubit thing. That was a colleague wanted me to keep that in there, but whatever, in the title. Quantum is a bit different than classical because of quantum mechanics. And so it kind of holds us back in what we can do. And it's kind of actually amazing that we can still do quantum error correction given all the limitations that quantum computing are correlated. You can also have leakage where it takes you outside of the qubit subspace and so on. But for the most part, we only have to deal with poly errors. And we can see, we'll talk later about why that is. Yeah, and just mentioning that there's many factors why quantum computing is so noisy, due to the environment, due to trying to, finite precision in your ability to control stuff, as well as potentially if qubits kind of talk to each other, that's not great. So, quantum computing is just inherently sort of noisy. If it wasn't that way, then we'd see quantum effects all around us. So we really need to isolate these systems in order to actually make use of the weird nature of quantum computing or in quantum mechanics. We also have to deal with the annoying thing called the no cloning theorem. So that means basically for a general state, you can't create a perfect copy. If you've taken quantum computing classes, then this, you would have heard about this pretty early on probably. But yeah, so we can't just copy like we did with the bits where we just copied, went 0, 0, 0, and then 1, 1, 1. We can't just copy that. We have to do something smarter and different. We also, of course, have to deal with measurement collapse. So if we measure an observable, it projects us to something, like Ben talked about. And it'll effectively collapse us to a classical state, effectively, for that observable. Well, you'll be in a definite state. And that's not good if we're doing a general computation. You want to have that, you want to keep on having this quantum evolution. So you can't just collapse it. That would be bad. So you need to figure out ways around that. For example, measuring operators that don't collapse, don't learn about the logical information. There's other operators maybe you can use. And then, annoyingly, also, it turns out there are no-go theorems that clever ways around these no-go theorems. And we'll talk maybe potentially briefly about those. Let's see. Yeah. Oh, and also you have to, because everything's so noisy, you have to deal with the environment, the qubits, the interactions. You have to make sure you do all this in an encoded fashion. You can't just constantly go to a logical qubit, sit around in that, and then go down. Back to bare qubits, do your gates, and back up. Because once you do that, you kind of have a giant hole in your whole scheme, and that's a place where your noise will happen, and that just gets mapped back to your logical space. So you have to do everything in an encoded manner. Ben already mentioned these using Cliffords in order to go from one sort of code to another code. So using these encoding circuits. So this is the way around the no cloning theorem. So we're not going to copy the state. Instead, we're going to coherently evolve it so the information is spread across other states. So for example, we start out with our qubit that's in some complex combination of 0 and 1. And then we use this C0 and this other C0 in order to spread the information. So we know with the C0, we have these set of rules. We can either think in terms of how it changes the polys, which we no longer have. Ben wrote that in terms of these states. In quantum error correction, we tend to think in terms more of the Heisenberg picture with the poly operators and whatnot. But we can see that if the control qubit is in a 1, then it'll flip the target qubit. So given that these states over here start out in 0, that means that this will only flip the other state and get a tensor product. And that would be kind of like, squeaky chalk. That would be sort of like doing the repetition code with copying. But, I went backwards. But we're not doing that. We're enlarging the basis states. So now I'm using the bars again, like Ben did. our logical 0 is 0, 0, 0, and our logical 1 is 1, 1, 1, but we're coherently entangled between these bigger states. The information is no longer stored in an individual state. It's spread across these 3 qubits. Let's see. All right, so we also would like to do something with these states, not just protect them. And we also need to, think about the logical operators. So a simple set of logical operators for these states, these stabilizer states, is to think about the logical x, y, and z. So logical x basically acts like a bit flip. So what's the logical, oh, okay. I did my animations in a different order. And logical z adds a phase to our state. So how do we get an effective logical x for a logical qubit? We just apply x 3 times. We see that it goes from our logical 0, which was 0, 0, 0, to our logical 1, which is 1, 1, 1. So this is our logical operator. Logical qubits are just like any other qubits. They're just encoded qubits on top of other qubits. So these are just like, or the weight 1 thing is our equivalent logical z operators. And also I'll share these slides out so you don't have to rush madly to write all this down, unless you want to. And then just like y is equal to ix, logical y is equal to I logical x times logical y. So you get something like this, for example, if you use the weight 3 version of the logical x and logical z. Okay, so how do we avoid measurement collapse? I already mentioned, kind of hinted at it previously. We measure observables that commute with the logical operators. So if it commutes, that means that we can kind of measure these things independently without disturbing each other. So we see that if we measure the observable ZZI or IZZ, both of these things commute with these logical operators. I mean, obviously it commutes with the logical Z operator because it's made of Z's or identities. But the X operator, we see that it anti-commutes twice, which is the same thing as commuting. And people understand what I mean by like commuting and whatnot. Okay, see a lot of heads shaking, good. Okay, cool. And so we can see also if we were to measure the logical 0 or logical 1, we get a +1 out for both of these observables. Also, for any superposition of these logical operators, you'll get a +1 out. So whenever we do the encoding circuit, we're preparing a state that's a +1 eigenstate of these observables, these parity or these stabilizer generators, like Ben mentioned, or there's sometimes called or whether if we measure these observables, will they project us to something else? And they won't. So this state is good. So Ben already showed kind of a circuit like this. Here is, I won't go too deeply into these circuits. In my second half, I'll basically go through this in a different way. But just to give you an idea of how might you measure these observables, what you often do, and this is not necessarily the only way, but you often include an additional ancilla and then entangle it using C-naughts or some other operation. So this is the circuitry that you might use in order to measure this observable ZZ. And then we'll later explain that in more detail why that works. And here's more circuitry. I'll quickly go to more an abstract version of this. But so here we see the encoding circuit at the very beginning again that produces our entangled alpha times 0, 0, 0 plus beta times 1, 1, 1 state. And then we use this circuitry to measure the observable ZZI. And then we measure this observable, or we use the circuit to measure this observable here. So you can, we introduce these two ancillas, or we could reuse the ancilla if we can reset it. we can see that if like an X error happens, Ben mentioned that like if you have a C naught, if an X occurs on the control, then it'll propagate forward and branch like this. So you get an X, X. And from measuring what should have been a plus plus outcome to a minus plus outcome. So we don't measure the state directly, but we measure observables that can help us infer what might have happened. There could be other error combinations that could lead to the same like change in these measurements. Sometimes these measurements are called syndromes, because it's kind of like you have a disease and you want to know the syndrome or the symptoms that the person's experiencing. But yeah, these help us infer what's going on. And this is exactly the same picture, but I abstracted everything away. You can ignore the circuits. So we see if an X happens, it will anti-commute with this observable. Ben already went through this, how like the new stabilizer gets updated by doing U dagger. So we just apply X to this ZZ operator, and so it anti-commutes. So it just flips the sign of the measurement. So it went from +1 to -1. Yeah, and that's just showing if you had like 2 X's, it will anti-commute twice, and so you'd still be +1. But anyway, so if this X happens, it anti-commutes with this observable, so it flips the outcome, and so we get -1, +1. So I'm just showing 2 different ways that you might reason about this sort of thing. And it's probably easier to just think in terms of diagrams rather than worrying about how you might implement it. But anyway, if an X happens in the middle, it'll anti-commute with both of the observables, so they'll both be -1. So that kind of pinpoints to, oh, okay, this is the most likely error. It's most likely that a single weight error happened rather than maybe a weight 2 or weight 3 thing happens that triggers this. And likewise, kind of the reflection of the previous example, if you apply an X to this qubit over here, it anti-commutes, so you get +1, -1. And so from this set of results, given the most probable thing is that single error with the faults. So in quantum computing, that's another thing. Everything's probabilistic. That includes quantum error correction. So you always have a probability of fixing things. You never can know for sure whether you did it or not, because you don't know what the environment did. This is showing just an example where, okay, if 2 X's are applied, anti-commuting twice with that observable is overall a commutation. It commutes, but it anti-commutes with that left side. And so, if you were to look at this table, oh sorry. I've switched from, in the table, I'm using 0s and 1s, so 0s for +1 and 1 for -1 observables. So just a different, different way of encoding this stuff. So if you're using bits, you usually use 0 to mean +1 and 1 to mean -1. Anyway, so if you look up in this table, this -1, +1, which is equivalent to 1, 0, it says to correct the qubit over on the left-hand side. If you do that, you just applied a logical operator. So it flips the outcome. That's not great. So yeah, so that's the problem, that you don't know exactly what the environment does. Sometimes the environment does the less probable thing, and you end up screwing up the system. But there's no way to tell the difference. And then, of course, if a single Z happens, a Z fault happens, then it adds a phase. It's a logical operator. So everything commutes with it. You don't even get a sign that something might have gone wrong. And so that's not great. This code is a classical code, so it can only deal with bit flips. Or you could do a version where it only deals with phase in a way that is non-destructive to the qubits, because we want to make sure that we don't project it, into a classical state. We want to keep on doing computations with it. But in the end, if you want to do effectively the logical version of, a measurement that's destructive, then we can just measure the bits in the Z basis, and it effectively collapses you to the classical version of the repetition code. I mean, this was a classical version, but in a quantum system. But this will make it an actual classical, zeros and ones. Yeah, it'll collapse you to a classical repetition code, but you can still use the same sort of lookup table for the classical version. This time, by taking the parity of those bits. Taking the parity of bits is the same thing. I don't know. It's a lot of, okay. So taking the parity of bits is the same thing as taking the XOR of bits. So the XOR is, so if we have input A and input B, and the output, it basically gives you the parity. So if both of the inputs are the same, then you get a 0. If either of the inputs are, or if the inputs are different, then you get a 1. This is the same thing as the parity. If you get an odd parity, it says yes. If you get an even parity, it gives you an even number, 0. So you can take the parity of the same, bits, here and here, and here and here, associated with those qubits, and use the same code. Nothing happens here. We get 1, 0, so that says, okay, flip the first bit, and the measurement was 1, 0, 0, so it says, flip the first bit here, you get 0, 0, 0. And then you can do the majority vote if you want, or you can also XOR the entire string, and you get 0, and so on. So these rules turn out to be effectively the same thing as majority voting. It just kind of encoded in a different way. So you could have used this instead. They're equivalent. Oh, and there's the table for the XOR stuff. That's great. Okay, plenty of time. So now the shortcode. Okay, and this will be the last thing really that I'll cover. So it's all been pretty, basic introduction to how quantum error correction works, as the title said. So we need to deal with X, Z, and Y noise. Well, Y is a combination of X and Z. So really, if we can deal with X and Z both, then we can deal with Y. So we only really have to worry, X and Z generate Y. If you think in terms of the poly stuff that Ben was talking about, they're generating set for the single qubit poly group. If we wanted to deal with Z faults, then we could have just done the where we take the encoding circuit of the bit flip repetition code, and we just slap on Hadamards, because Hadamards change you from the Z basis to the X basis. And then the observables that you would measure would be XX, XX. And that would allow us to deal with the Z phase flips. However, bit flips X's commute with these observables, so we can't detect them. To go into this, I think Ben might dabble with this in his next talk, but there's more explanation in both the QEC textbook that was edited by Ladar and Brun, as well as in Nielsen and Schwang. But effectively, for any unitary, you can kind of think of it as a complex linear combination of the poly operators. Just like states are complex combinations of the basis states, these poly operators are effectively a basis set for unitary operators. And so once again, just like if you can deal with X and Z errors, then you can deal with Y. Well, if you can deal with X, Z, and Y, then effectively this is kind of like the different histories of the possible errors that can happen, and you can deal with any unitary errors. So you can deal with arbitrary unitary errors. It's kind of hand wavy, but there's more proof in those books. I don't really feel like going through all the math. Okay, So how do we deal with both X and Z? So Shor, who's famous for the Shor's algorithm, in 1995 came up with this Shor's code. I think Steen might have come up with the Steen code around the same time. I think maybe it was accepted to a journal a little bit later in 1996, but they're all dabbling in the same sort of idea. People were very, kind of poo-pooed quantum computing because it's because of the inherent noisiness of it back in the day, and they said this will never work. And then the field of quantum error correction was, worked out slowly, but they're able to find ways of, actually, doing quantum error correction. So that kind of dealt with those naysayers. You just slap on Hadamard's at the end. So we have the encoding circuit right here for the phase flip code. And then for each one of those qubits of that original encoding circuit, we then apply the bit flip code. So we take those individual states and we then encode it into the bit flip code. To kind of see that better, so here's our original logical 1 and logical 0 states here. And then we can see, because of this, to do the plus version, logical plus version of that, you'd have this state. Because in general, the Hadamard, I was writing the Hadamard. The Hadamard on 0 is equal to the plus state, which is the same thing as the square root of 0 plus 1, which you've seen a bunch of times. Maybe I even wrote it. OK, no, I didn't. Well, actually, maybe I did in a bit. But anyway, yeah, this is just taking this thing and substituting 0, 0, 0 here and 1, 1, 1. So that's the logical version of the plus state and the logical version of the minus state. So if we started out with this state, then let's see. Actually, I have some. OK, yeah. If we started out originally right here. This is just the normal bit flip encoding circuit right here if we ignore the Hadamards. And then we apply the Hadamards, we get plus, plus, plus. So if we're trying to encode 0, we go from 0 to 0, 0, 0. And then applying the Hadamard, you get plus, plus, plus. So that's, there's the definition of that. So that's kind of the red box there. And then if we apply these encoding circuits here, then it will just convert these pluses over to this state. So the 3 copies of this state, which is nation. Now, it's kind of funny in the quantum error correction book when it's talked about. Dave Bacon, who's a famous QEC person, had this quote. I guess he found it really beautiful, which is funny that it's in a textbook. Anyway. So here's the logical operators and the stabilizer generators. It's not really important. You can kind of see that it kind of looks like the repetition code. So we were measuring these sort of observables for the bit flip repetition code. So it kind of looks like a bunch of bit flip codes here, and then with some X stuff down here. And then we can see so these columns represent qubits, and the rows represent the individual stabilizer generators. And so if we were to apply an X to the first qubit, then we can see that this stabilizer generator that we would measure for the Shor code anti-commutes with it. So it's able to detect an error has happened. Likewise for Z, it anti-commutes with this stabilizer generator that we'd measure. Y, it anti-commutes with both of those things, and so on. I didn't, anyway, you could do all combinations, and you can see that it uniquely sets off different stabilizer generators, or different combinations of them. So to detect these things and uniquely identify the weight 1 errors and therefore correct it. So it's it's a distance 3 code. Because it can detect 1 error. If it was a distance 5 code, it could deal with, or one fault. If it's a distance 5 code, it could deal with 2 faults and so on. Anyway, sort of ideas apply. You know, we need to not just measure these observables and come up with corrections, but we need to do some encoded operations. So you might think about how does that happen, and we might discuss that in later talks. How do we deal with faulty measurements? So if you have some probability of the measurement going bad, what does that look like? What do you need to change how you measure things and how you approach this? And so far, we've only been talking about noise faults that have been injected before the parity measurements that we've been making, these observables that we've been measuring. So, you know, we can see that they can deal with those things, but what happens if we think about noisy operations? So if the faults are injected inside that circuit, what does that look like? And we'll talk a bit about that as well. So stay tuned for Ben next hour.
Are there any questions? Okay, let's take a break for a few minutes then.
Distance 5 is awesome. Thank you. Awesome. Thank you.
I just wanted to say I found it really interesting and kind of funny you mentioned the book by Bruno Ledar, because I'm taking classes with both of them right now.
Oh, nice, yeah.
I found that funny.
Yeah. Yeah, it's a good book.
I've read that thinker.
Yeah. Yeah. Can be a little chaotic though, since it's about by a bunch of different authors, but yeah, it's a good resource at least. Yeah.
I'm doing my master's at UC right now, so I'm taking multiple.
You should discover.
There are internships probably too that you might want to consider. Yeah. We do have a master's, or someone who got a master's doing quantum error correction, so it's not necessarily a requirement to get a PhD, but it's usually in physics largely expected, but it's still possible. Yeah. Probably not here.
And after at the last lecture, we will open the Zoom and the YouTube.
At various times, so.
For error correction, probably not. You're better asking you guys.
Okay, we are in. That's wonderful. Because I will. You will have just to stop the stream on YouTube and the recording on Zoom. Nothing else. We will start. We will start with. Because we are doing streaming. So I will prepare the streaming.
Let's see what.
Hi. Here now. And later I can here I prepare you the stream. You will be in a view,
You'll see exactly which one. It could be.
and after you will have to
I mean, it's
push end
possible
stream
that maybe I
Okay.
messed something
and
up.
stop in Zoom the recording.
Okay.
Not now.
But it's
Because
super.
I have to change some configuration in the next pose.
Okay.
Okay?
So stop screen and then assume.
The most important thing is that I was able to log in now. Yes. And you have just to stop the stream, stop the recording, and close the Zoom, and end this button.
might
And
have
you open just
Here, okay, so this is
minimize
assuming that no error
just
has
stop
occurred.
here. You'll find end the
So
stream.
they
Nothing
usually
more.
start out
noticed you have
by
quantitative
definition
life sciences
in
account.
+1 eigen.
The right account.
Okay, so this is the definition.
Sorry?
Yeah, yeah.
Yes, we have
Yes.
account.
So this is the quantitative life sciences account.
After the accommodation.
We're doing like
Yeah,
physics today.
yeah, you can see if
Sorry?
like you were to
So
look
if you
at,
click on
you
that.
know,
Yes.
says
you know,
quantitative
if you
life sciences,
were to
like
measure
biology.
the
Yeah, but
Z
Is
both of them would get a plus one.
This is the channel that we
And so you get,
we're asked to
as
do,
well as for this
and it will be
so you
copied
get
on
two
the other channel
minus
of
ones, which is a plus one. So
I think
these
it was
two,
Compositionality.
you can see stabilize the state. And so
the
yeah,
playlist
since
will be
it
copied
stabilizes
also on
the
the
state, then it would
You
be
have to do it
plus
both.
As long as it's the one you
But
want.
in that slide, we are doing the
It will be
combination.
both in two
channels.
channels.
Yeah, we're playing
I think the other is
errors too.
Compositionality.
So sorry.
Yeah.
So the error ends
guess
up
it's kinda
like
sorta like
flipping
an
the state.
No,
Yeah.
I mean, we have mathematics,
Yeah, no
instrumental, artists and physics, quantitative life science.
I'll probably leave this here.
High energy.
Do I have time to get up to the bar?
Oh.
Quick?
I was supposed to end at 5:40, and so he was supposed to, 15, sorry, 15:40. So it should be 15:50 that you're supposed to start, I think. Yeah, 15:50 is when it's supposed to start.
Yeah, 3:15. Quick.
50, so we are in time.
I've written my own simulators that are really fast. So you can look up my stuff, but the basic thing that a lot of people use is called CHP by Asman and Scott Aronson. So this is and I have a more complicated version based on this, but it uses sets to represent these things, so you no longer represent, because usually you only have a few ones either in the column direction. Yeah. So effectively, I have a version that represents things like row-wise and column-wise sparsely, and then you figure out how to update these appropriately in an optimal way. You update each other with each other, and it's even faster. Yeah, I have like two different basically like the list of stabilizers that have the qubit in it. One of them has a sense of these, so these are and then it lists the qubits, and this one it's the qubits and it lists the stabilizers. The qubits that have, so if you wrote out like a matrix.
Like the data qubits.
Yeah.
I see.
Yeah. So it's code, it has both a C++ and a Python version of it, but you can, this will link you to the GitHub that has the code. Effectively, I was trying to implement CHP in Python, and it was super slow for large codes. And I kept on messing with it, and I didn't realize I was doing something smart, but whenever I analyzed the complexity, it was actually much faster.
Nice.
Yeah. So sometimes writing things in Python, you stumble upon better algorithms. No, I don't, but I'd like to keep.
On Thursday, so.
Yeah, I don't personally, but it does seem to be sort of a useful thing for quantum error correction, at least like for. Yeah. Yeah, for at least in quantum error correction, it's useful for. It's probably useful for like lattice surgery, how to optimize that and stuff. So someday I want to learn it. Just too many things to learn. Yeah.
I was curious because I'm doing some research trying to use
You have both the Dodo book and the new one that they put out, but I haven't really read it. There's a the giant textbook with a Dodo on it, and then there's it's by what's his name? The guy in our company. Bob, yeah, both of them. So there's a newer one too that's supposed to be more aimed at like high schoolers and stuff.
Okay, save.
All right.
A little messing with the mic. All right, and we're ready to go.
Yeah. All right. Welcome back for lecture 3. And we have Ben Krieger again.
Nice. All right, so is it enough to have a code that can just detect and correct Pauli errors? It is, and I will coherent rotation by a Pauli that is itself correctable, right? So maybe some of you know already, probably most of you know, that like I can have u p theta equal to some exponential of I times a Pauli times theta, some angle, right? This is going to be some unitary operator, and you can do a bunch of Taylor expansion, and knowing that the square of a Pauli is the identity, to get that this is cos theta times the identity plus I sine theta times p. So it's just some linear combination with complex coefficients of operators. One of them is a Pauli. What would happen if we applied this unitary to a stabilizer state that was stabilized by some stabilizer S, and then we measure S, and we assume that S anti-commutes with the Pauli? Because spoiler alert, if S commutes with the Pauli, nothing happens, right? So let's set up S times cosine of theta identity plus I sine theta p acting on psi. Do we even need this thing? No, sorry. We're going to project into one of these two spaces, right? Either the +1 or -1 projector, right? So we expand out. This is going to be equal to cos theta I plus S, I plus or minus S over 2 times psi plus I. Yeah. P sine theta I minus or plus, right? Because these anti-commute over 2 psi. Right. So a +1 outcome. Then this cancels out completely, and the resulting term. Well, okay. So let me write this down. +1. This will cancel out, and you'll get psi. Once you normalize, right, the square root of pj, et cetera. And then -1, you'll get some term sine squared theta, p acting on psi. So whenever you measure a stabilizer that anti-commutes, even though there was some coherent rotation, right, the error is not just some Pauli that you apply. The projective measurement collapses you into a space that's spanned by vectors that are Paulis acting on the original state. And you can just continue with your regular error correction formalism from there. The full proof that like you can correct arbitrary dynamics is more involved, and it even involves non-stabilizer codes. And if you want to know more about that, you should look at chapter 2 of Brun and Lidar. The book they edited. Yeah, well, okay, I would say they wrote the book on quantum error correction. They didn't write the book, they edited the book, but it is also called Quantum Error Correction. Right, and there's like a teaser for the more general applicability of these stabilized codes. Okay, so all this is to say that it is enough to correct Paulis. The remaining question should then be, how many Paulis can you correct with a certain number of qubits? Oh yeah. So Kiran showed in the last lecture that we can do it with 9 qubits. It says nins qubits in this PDF, but that's a typo. Can we do better? The one way to answer this question is by imagining that each possible syndrome, right, every list of plus or minus ones or zeros and ones that you could get out of measuring your stabilizers corresponds to some unique Pauli error, which is just the weight of a logical operator, the minimum weight, right? It's the number of things that have to go wrong before random dynamics have flipped your qubit completely and you have no chance of detecting it. So you want high D, high K, low N. For a code with K equals 1, right? So if you have an N1D code, then there are N minus 1 stabilizers. And you have, right, and the number of things that can go wrong, the number of Pauli operators, is 3 times N, right, X, Y, and Z for each N, plus 1 for the identity. Right, the identity, if nothing goes wrong, that has to give you a unique signal that's not the same as some error. So, you have to be able to successfully get that nothing happened. Oh, the number of bit strings that we can measure is 2 to the N minus 1, right? So the number of syndromes has to be greater than or equal to the number of errors that can occur, which is 3N plus 1. Whenever we have a discrete equation like this, I'm not going to try and do algebra. I'm just going to start plugging in values. Right, well, okay, it doesn't make sense to have N equals 0. What about N equals 1? 1 is not greater than 4. What about 2? 2 is not greater than whatever this is. If you keep going, you'll note that the smallest value for which this equation can be satisfied, this inequality can be satisfied, is 5. N has to be 5 or more. And as it turns out, there is a 513 code that it just barely makes these equations. It's got 16 possible stabilizer syndromes, and there are 16 things that can go wrong, because 3 times 5 plus 1 is equal to 2 to the 4. And here are the stabilizers, X, Z, Z, X, I. Right, so S, 5. And its logical operators are, well, there are weight 3 logical operators, but they look ugly. So I'm going to write some first using ket notation before the stabilizer formalism was invented. So there really were people out there messing with 9-qubit kets. Luckily, Daniel Gottesman saved us from all this, and we don't have to do that anymore. Now we can add all kinds of overhead and still say that we know what we're talking about. Again, double-edged swords. Oh yeah, and we mentioned that the number of correctable errors is roughly half the distance, right? If in this distance 3 code we were to have 1 error, we could assign a unique syndrome to it. But if you multiply that error by a logical, you may get a weight 2 error that has the exact same syndrome. So you say is less likely, but less likely is not impossible. So there's still going to be some finite probability of failure, no matter what code distance you use. The hope is that we decrease the failure probability exponentially in the amount of overhead. All right, so that's one code. Kiran has used it. Did we do anything with the shortcode? Not yet. But the rest of the talk is basically going to be about what kind of codes you can construct and how easily. So, should I talk about classical coding theory now? No. First we're going to do, single check. And or iceberg. Right, so it's got n minus 2 logical qubits, right, which is a very large number of logical qubits. That's like the maximum you can have. But it's only distance 2. And you'll see why. Its stabilizers are x. I'm going to use the oath of where that error happens. So you can tell that something has gone wrong, but not where. And that's why it's distance 2. Right. So there's one construction. These codes get used all the time, and they get used to construct bigger and better codes. So it behooves us to know about them. OK, now we're going to get into what Kieran was talking about, concatenation. Concatenation has got to be my favorite code construction. And it generalizes, it does all kinds of stuff. There are rules that once you learn them, you can break them. Concatenation is lovely. So what we saw Kieran do was take, the encoding Clifford for a single code. Here it's got one input wire, right? And what comes out is some, 3 qubit state. And then we take all these out here. We encode each of those qubits into some new code. And with this nice tree-like diagram, we can start to synthesize bigger and better codes that way. When do we do this? OK. Let's imagine doing this to 2 arbitrary codes. Oh, where's that cloth? Here we go. Get rid of this thing for a second. So concatenation is going to be used to take low-level code, which has NL, KL, and DL, right, for low level, and a high-level code with, predictably, NH, KH. Qubit, you need a low-level block. KH, KL, let's see, because, that's right. For every physical qubit of the high-level code, you need an entire block of the low-level code. So if your low-level code encodes like 6 qubits, and you want to encode into a 513 code, then it's not enough to take 5 qubits out of the 6 qubit block and put them into the encoding circuit, because your Paulis will get messed up and it will not work. We can get into it later in the Q&A if you like. What you have to do is get 6 blocks of the 513 code that you want to use, like this guy, and then take 1 logical qubit out of each of your 6 logical qubit blocks and feed those in independently. And that's basically to ensure that in order for something to go wrong at the high level, it has to go wrong on separate blocks at the low level. Actually, OK, we can see I can see people are getting confused. So I'll give you the nucleus of this. So you have x1, x bar 1, is equal to xi, xi. X bar 2 here is equal to, let's see. Let me go xii and xi. OK. If I was to multiply these operators, I would get ixxi. So if I want to flip one of the logical qubits, then I need to flip 2 qubits. If I want to flip the other logical, I need to flip 2 qubits. If I want to flip them both, I need to flip only 2 qubits. I don't have to flip 4, right? So things go wrong at the logical level with different relative probabilities than they go wrong at the physical level. And so if you take, at least in this naive construction, for every physical qubit of the top-level code. And of course, those physical qubits are replaced by KH logical qubits in every block, so you wind up with KHKL. The benefit of putting up with all that rigmarole is that you get DH times DL, right? So you can, when you want to construct higher distance codes, right, something with distance bigger than 2 or 3, you can start taking products. Now, okay, I wonder if I should draw the circuits. Nah, I will leave figure 1 for people who are looking ahead in the notes here as soon as I post them. But I will write out the stabilizer of the 422 code concatenated with itself. Right, so if I take this 422 and concatenate it with itself, I wind up with a code that was in a paper in 2022, I think. The Prabhu and Reichardt distance 4 codes paper. Okay, so this is now state of the art. It may seem confusing, but you're now doing legitimate, up-to-date research. All right, stabilizer of this code. Let me start at the top for some reason. It's going to be x, 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 z, 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 You can see that even though it's not exponential, a quadratic amount of work can still be a lot. Also, a lot of your Paulis wind up being sparse, right, affecting relatively few qubits. Now there are 8 logical operators to worry about. Oh, actually, sorry. We're not even done with stabilizers yet, because this is just 4 independent blocks of the 422 code, right? And you can see that because these columns have identities below them, identities in the rest here. This is, completely unentangled blocks. So this is distance 2. If I apply 2 errors here, I flip one of these qubits. And I don't have 4 qubits yet. I have 8. So 4 logicals, I have 8 logical qubits right now. And what I have to do in order to finish the construction of the concatenated code is write the stabilizers of the top-level code in terms of the logical Paulis of the bottom-level code. Okay, right? So this is like you can do whatever you want with these logical Paulis. They act just like the physical Paulis. One thing you can do is take tensor products of them and make stabilizers. Okay. So luckily, I have prepared this earlier, right? So here's, right, x, I, x, I, x, I, x, I, x, I, x, I, x, X, I, Z, Z, yep. Logical operators. I can sense the boredom. Kid. X4, IX, IX. Ba, 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 All right. Have I done all of this for absolutely no reason? No. This is all to demonstrate that even though we've gotten sort of fully up to date with state-of-the-art techniques in the first lecture, constructing these tableaus, it gets cumbersome pretty quickly. You want to get a computer to do it if you can. This is a hackathon. You can maybe try that in the hackathon if you want to. Also, this is why you often see quantum error correcting people work on little esoteric diagrams. Slow operations like the ones I do with my clumsy human brain and hands, right? Makes sense to do quadratic speed up. We can draw individual blocks of this 422 code. Let me put qubits on these little circles, and I'll have 16 of them in total. And if you stick them on a square, then they divide naturally into 4 groups of 4. I can also draw, well, okay, so I'll say that there's an SX and an SZ hosted on each of these squares, and you can see, obviously that it's 4 qubits with 2 stabilizers, therefore it's got 2 logicals. You can even interpret the logicals geometrically, right? You can put an X bar here, and you know that the anticommuting Z bar has to go over here, then you can stick the other X bar up at the top, right? Or you can multiply it by the stabilizer so that it overlaps on both qubits, but because it overlaps on both qubits, it commutes, right? And you can stick a Z bar over here, right? And you can begin to say, oh, I have these face-like stabilizers and my logicals are on the edges, and you can start reasoning geometrically. Like, for example, when I want to produce a weight 4 stabilizer, right, on these tiles out of logical operators, I can use X bar, X bar, X bar, and X bar, right? So I can have vertical X's and create this sort of octagon in the middle. And I can have Z bar, Z bar, Z bar, Z bar, and create a little tile that crosses it. And because these things overlap on 4 qubits, they also commute. And I can also do, because there's an X that I can bring down here, X on this big octagonal tile and a Z on that big octagonal tile. And that completes the stabilizer group, right? Which is a lot easier than writing out a bunch of identities, bar 2 and Z bar 1, right? So Z bar 1 and Z bar 2 commute because where they overlap is both Zs, but the other ones intersect on points. And I will also have logicals going down the sides of this lattice, right? Z bar 3 and X bar 4, and X bar 3, Z bar 4, right? Much more succinct, much more compact notation. You can see everything is length 4. If you wanted to, you could check out what, this is something that we're in the middle of at the office at the moment. If you permute these qubits, there are some permutations that preserve the stabilizer group, right? Like if I were to pick this entire lattice up off the board, flip it and put it back down, you wouldn't be able to tell, right? The stabilizers would look the exact same, but some of my logical operators would move around. This thing would move down here, this would move up to the top, and you've got to wonder, whether there would be any non-trivial logical gates that you could do just by permuting the qubits, as you can do with really high fidelity in an ion trap. There are more pros and cons to concatenation. Okay. One of the pros is that if you're in the scenario where you measure stabilizers perfectly and you learn some syndrome, then there's a decoder where you basically decode the low-level code first by brute force adding up every probability of every Pauli and assigning them into groups. And then you proceed up to the next level, and you basically iteratively decode this gigantic code, right, without ever having to consider all of the probabilities of all of the 6-qubit Paulis, right? It sort of divides the decoding labor for you, and you can get an optimal statistical decoder that gives you soft decisions. There's a paper from 2006. I think one of our projects, I'm in charge of the projects, one of our projects is replicating the results of that paper. So, I mean, not state-of-the-art research, it's 2006, but you know, what you can do in a week. Okay, cons of concatenation. Why don't people use concatenated codes all the time? One, you do want to use a distance 3 code because you don't have that many ions in your trap. So you can't afford lots of overhead, and you want to see how well you can do at low distance, which is still pretty well. Also, as you add more layers, right, your distance grows exponentially, but so too does the number of qubits. And so it's not very long before you're dealing with tables that you can't write down, diagrams that you can't put on the board, and things get really cumbersome. And so we're going to go to even more formulaic code constructions. So instead of beginning with, all right, so we're going to the next section now. I will do one of these. So CSS. The CSS construction for quantum codes. This is another one of the pre-stabilizer constructions that I'm going to do in the stabilizer formalism just because it's easier. But if you read original work from the 90s, like the guy takes a classical error-correcting code and puts a ket on it. It's like nuts. Speaking of classical codes, I now need to do classical coding theory in 10 minutes. There's a lot to classical coding theory. We're going to do a very small but very popular subset, which is linear codes over F2 coding theory. Classical code typically has a parity check matrix called H and a generator matrix called G, generator, such that, let's see, in this lecture, H times G of T will be equal to 0. The rows of G will be your code. If I took 1, 1, 0, right, I would have 1 plus 1, which mod 2, because we're in F2, is 0, and 1 plus 1 is again 0, so this vector is also in the kernel, and those are the code words, right? So this would be H, and then my G, okay. G would be something like 1, 1, 1, where I think you're allowed to leave the all 0 string implied. At least that's what I've done in the rest of these notes. There are a lot of more efficient constructions for distance 3 classical codes. Well, okay. Those in the know already know which one that I'm going to pick. It's the 743 Hamming code. And this, okay, there's a clever trick being used here. If I want to know where an error is, right, and I'm going to multiply this parity check matrix onto the error string, right, well, I should mention that if I take some error, right, and I add some code word, and then I multiply by the parity check matrix, right, so these are each vectors. This is a matrix. It's all over bits. Well, okay, this is going to be HE plus HC. H times the code word. Code words are in the kernel of the matrix, right? So here I'm directly getting the syndrome of the error, right? No matter what code word I was trying to transmit, which is a property that will turn out to be very convenient later. So let's imagine that I want HE to be distinct on every weight 1 E that I could put in. Well, okay, so if I take some matrix and I multiply by 0, 1, and 0, then wherever this is, I'm just going to get out column J. So if I want to make a distance 3 code, classically, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and there we have 743, which is another NKD tuple, but there's no extra line here that denotes it's a classical code, and this is from Richard Hamming. Great. Why am I using this code? Because it has an obscure property also. Let me bring this in accordance with the notes by flipping the matrix front to back. H. Hamming. G of the Hamming code. Great. So it's got 4 orthogonal non-zero code words, which means you can get a total of 16 messages in there. And you can determine whether, given any 7-bit noisy string, whether it's equivalent to one of these up to a weight 1 error just by multiplying on this matrix. Cool, but these are classical codes. How do we promote them into quantum codes? Kieran showed us how to do it with repetition codes, and it turns out that that generalizes to any classical code. We're going to start with these parity checks, and when you multiply them on with some error, there's a question, where does the error overlap with the parity check? And if you start multiplying, now we can detect X errors that occur, in some arbitrary location. For example, IIX, III, right? You're going to get a syndrome because it anti-commutes with this check and this check, but not this check because there's an identity here, right? You're going to get a syndrome that's equal to the classical syndrome of putting a classical bit flip on this column here. You could do the same thing in the X basis. And these stabilizers commute. Is it guaranteed that they commute? If I was just to take some random matrix of zeros and ones, turn it both into z's and x's, and then stick them on top of each other, would the stabilizers commute necessarily? Sleeping guy in the 4th row. Do you know? Sleeping guy does not know. But the answer is no. In order to get these stabilizers to commute, the code has to be what's called dual containing. You'll notice that the parity checks of this code also appear as code words, right? These vectors are not only in the parity check matrix themselves, but they are in the kernel of that parity check matrix. Dual containing is a very obscure property of classical codes, but we can see that it's related to making the stabilizers commute. There are lots of papers where people construct CSS codes, right? This, by the way, is how you construct a CSS code. You take 2 classical codes that are related by, each one being in the dual of the other, and then you translate one of them to Z stabilizers, translate the other one to X stabilizers, stick them on top of each other. There are plenty of papers where you construct CSS codes, and they always do some weird, obscure stuff that you can never tell why it's happening. Normally, here's one vector, one code word of this code that does not appear in the parity check matrix. Sure enough, it becomes a logical, right? So your logical X bar, right, or your Z bar, right? These become X, 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 and Z, 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 Z. Huh? This was not as much of a mess as this thing. And these are also not minimum weight, but they're very symmetric. You can see that if I multiplied these 2 together, I would wind up with some weight 3x, right? And likewise, I have some weight 3 z that I can cook up. And they always anti-commute, right? And this winds up being a 713 code, right? So you're not using as many qubits as the short code. That's nice. And it gives you access to, it gives you sort of difficult access to a decades-long literature of classical coding theory. There are lots of tricks you can do. There are like product constructions, how to make the stabilizers commute. We're only going to do one trick, because it's the one I understand, as to how to make the stabilizers commute, and that is homological and topological codes. Anytime you're using a lot of words that end in ogical, that's how you know you're doing real science. What is the difference between homology and topology? I don't know. All I know is you get good codes. Actually, according to like the orthodox definition of what good codes are, these are not, according to like the orthodox definition of what good codes are, these are not even good codes, unless you use hyperbolic space, but we're gonna do all Euclidean. Let's consider an arbitrary graph. I don't mean a graph like a plot of a function, I mean like a diagram you would make of a network, right? So it's got vertices, it's got edges. Here's E1. There's another one, it's called E2. There's some other edges coming out from every vertex, and stop at one of the corners of the cycle, it has an incoming edge and an outgoing edge. So if I were to put qubits on these edges, and I were to put X stabilizers on these vertices, and Z stabilizers on some of the cycles, oh boy, they would commute. Pretty weird, but we will do any weird thing in order to make the stabilizers commute. Perfect. What is the N of this code? We don't know. What is the K? No clue. What's the distance? Hoo boy. But I've made the stabilizers commute. You have to add a little bit more mathematical sanity in order to be able to say what the N, K, and D of such a code are. Okay, and here's where I run out of material early, and we go into questions. But I'm sure there are going to be questions. Oh, let's erase this garbage. We're going to do another code that has like just as many qubits, but we will not have nearly as bad a time writing out stabilizers, because we're using topology. Let us imagine that the graph we select is going to be a square tiling of a torus. Torah code. There's a bunch of algebra that I should put here, but this diagram more everything. Okay. The Torah code is a special type of homological code. Homological codes are a special type of CSS codes. So you can see that we're drilling down from the general to the specific, and the Torah code is more or less state of the art. There are lots of groups working on the Torah, well, okay, on relatives of the Torah code that you can cut and stretch out onto one sheet, so you can put everything on a single chip. But the Torah code is close enough for government work. Here's how you draw a torus. Okay, that's, you know, if you go to like your, with X stabilizers that are weight 4 on these edges, right, X, 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 and we're gonna wind up with, where have I got a nice square? Here's a nice square. So sometimes you see these called plaquettes or faces or tiles. I will have Z, 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 Z. And sure enough, wherever one of these squares intersects one of the vertices, it always hits 2 edges. Now, let's see. I think the homological topological part of it is where you say, not all cycles in my graph are going to be Z stabilizers. Only the topologically trivial cycles, right, that don't loop around the torus, right? You can imagine if you were trying to pick up a kettlebell and you tried to like palm it, it wouldn't work. But if you grab it by the handle, that works, yeah? So if you grab around this, let me do a dotted line through here, right? So loops around here are gonna be logical operators, and there are partner loops that I can't draw in 3D, but I do know how to draw in 2D. So I'm going to do one more diagram, and then we're going to call it a day. Well, up to questions. Let's draw another torus. This is actually my favorite way to draw a torus. Okay, so again, we will have X stabilizers. By the way, okay, so this is if Pac-Man walked off this edge here, he would come back on here. And if it went over here, he would come back on over here. That's what makes it a torus, right? You can imagine these different cut edges are wrapped around so they fuse together. I, again, have Z stabilizers here. And you can read about this in chapter 19 of Ladar and Bruin. But Pac-Man is walking back over, right? If I put another X here, the thing moves again. And if I put another X here, this moves over here and cancels with this, right? So my logical operator is given by sort of like walking between sites of the torus, right? And I have this length 4 topologically non-trivial loop that goes all the way around one of the handles. Likewise, if I put Zs, right, it activates this vertex unless I put another Z, Z, Z. That wraps all the way around. And I can do the same thing on horizontal edges, Z, 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 and X, 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 to wind up with a, in this case, 16 to 4 toric code. But in general, n squared, or sorry, let me go d squared to d. Because you can stretch the dimensions of the torus, just tile a bigger lattice, and get whatever distance you want, 3, 4, 5, 6, 7, 8, 9. Very granular. And the stabilizers are always low weight, so they're easy to measure with circuits. And that's what makes this code, you know, a nice high threshold option for near-term memory experiments and state-of-the-art stuff like that. So, given that, I will end a little bit early, and we can take 10 minutes for questions or whatever other topics you are interested in quantum error correction. The crowd is bummed now.
I know.
These people are ready for dinner.
Oh my.
My God.
I'm gonna have to wait a little longer, but before we have dinner and
Good
another
luck, Kieran.
session, let's have some questions. Okay.
Long story short, with CSS codes, there's a transversal CNOT. So if you can run a CNOT between qubit k in block 1 and qubit k in block 2, and you do that for all k, then as long as you've got 2 blocks of the same CSS code, then all of the logical qubits become in block 1 become entangled with all the logical qubits in block 2. And that's for block-to-block entanglement. If you want to generate entanglement within a block, you can do that by hook or by crook. So there are some codes where, actually, okay, I should have got this paper done before I came here. But we have a paper coming out in a little bit where we have a code on 8 qubits that sit on the vertices of a cube. And if you flip the top face, it does a logical CNOT between 2 of the logical qubits. So that kind of thing happens sometimes. There are also gates that you can do in, well, okay, some people call this fusion-based quantum computing. Some people call this lattice surgery, although it doesn't always involve a lattice. But if you can measure projectively a joint logical operator, then you can project the system into a subspace. Well, okay, and if you begin with an extra stabilizer that you don't need, you can measure operations, right? Always measuring something that anti-commutes with your current stabilizer, and gradually your logicals become different, right? So you can execute a logical Clifford by doing these repeated anti-commuting measurements. And you can do that within a block as well, provided that your code has reasonably low distance compared to its stabilizer weight. Otherwise, you're gonna have to use really ugly circuits that propagate errors in bad ways, and it won't work. But for a distance 4 code with weight 8 stabilizers, it ought to be fine.
Thank you. And sorry, one more question. So
the fact that the number of logical qubits here is constant, right? There's always 2 logical qubits because there's only 2 ways you can go around the whole of a torus. In order to create families of codes with what's called constant rate, where the number of logical qubits is in a constant ratio with the number of physical qubits, which is a lot better, right, than having just a constant number of logicals. You can use manifolds that have hyperbolic characteristics, right? So they're sort of like lettuce, right, where they get very curly towards the edge because most of their bulk is near the boundary. And, well, okay, lettuce is not closed up into a torus, but if it was, then you would observe that you need many holes in order to connect all of that boundary to itself. And those many holes produce many logical qubits. Let's see. What were we talking about?
Symmetries and how it plays a role in finding these different stabilizers.
Yeah, let's see. Are hypergraph product codes like really symmetric? I don't think, yeah, I don't know. But yeah, and symmetries also play a huge role in finding logical gates. So if you want to show that there's some logical Clifford or non-Clifford, then like advanced symmetries other than just, the Pauli group and the Clifford group can come into it, for sure.
Thank you.
Thank you. Other questions? Okay. Oh, you make me run.
Yeah, okay.
Where was that?
I was just wondering, is there any proven, I guess...
Like we do at the office, you wind up finding that these codes are like equivalent to each other under certain transformations. So, for example, there's a way to construct the Steen code from a 5-qubit version of a cut-up toric code. There's a construction of the 5-qubit code from the toric code where instead of, so some people are crazy, and instead of putting the boundaries here and here at 90 degrees to the lattice, they'll make a grid that's sort of like this, and then put boundaries like here. And if you do it right, I haven't done it right, but you can arrange it so that these 4 corners each have an edge coming in, and then there's one square in the middle, right? So it looks kind of like this. And that gives you a code with 5 qubits that's still topological. And it turns out to have the same stabilizer group as the 513 code. Is this important? Nobody knows. But yeah, should we be using CSS codes or non-CSS codes? Hard to say. CSS codes have, in general, probably a little bit worse rate. And the influence of that property on doing actual error correction in practice, not well understood. There are some pros and some cons to it. CSS codes tend to have more logical Cliffords. So they have logical C-naughts from block to block that you can do transversally. Non-CSS codes don't always have those. So you wind up having to use more awkward and clumsy constructions when you're trying to get a logical C-naught. You can do phase, the remaining Clifford, nobody's favorite Clifford. As long as your generators are weight 0 mod 4 with CSS codes. So you can get all Cliffords transversal, and transversal gates are extremely reliable, especially when you're talking about transversal single qubit gates, right? Single qubit gates have huge fidelity, and if you need 2 or more of them to fail in order to produce a logical error, when you're writing out a logical computation and you have transversal single qubit Cliffords, you can more or less ignore them, right? You can act like the error rate is 0 for the purpose of calculating actual failure rates in a device. So those are all arguments in favor of CSS codes. Yeah, and then I guess the argument in favor of non-CSS codes is you can save 2 qubits. But, I mean, you'll notice, all right, 513 beats 713, but 1644 beats 513, because I'm, on average, using 4 physicals per logical, and my distance is 1 unit higher, right? So if 2 errors occur, I'm going to be able to tell. And it's like, Donald Rumsfeld, unknown unknowns and known unknowns. A known unknown is a lot better than an unknown unknown. So if a weight 2 error happens in a distance 3 code, and you think a weight 1 error happened, then you correct and you put in some unknown logical operator, you've sabotaged the rest of your computation. You might be doing a million more gates, but you've destroyed your state very early on, and it's all wasted effort, and you have no idea. With an even distance code, if 2 errors happen, then in principle, or with the distance 4 code, if 2 errors happen, in principle, that gives you a unique signature. You can say, I don't know what to do, right? It's like getting an error message rather than having some thing that you think is not a real error, you think is correctable. So you can stop the computation and start again. Or at least post-select out those garbage runs from whatever subsequent computation you're trying to do on the output. And that can be used to increase, like...
Makes sense. Thanks.
Okay.
There's also a lot of people that will use like codes that are not quite CSS, but are locally Clifford equivalent to a CSS code. So if you see like Clifford deformation, normally that's being applied to a CSS code to make the stabilizer something other than all X's and all Z's, but you still get the same divvying up of error correction gadgets, and you still get the same logical gates. You just have to undo that weird Clifford at the beginning and then redo it at the end.
Okay, nice. So thank you. Any more questions? I think that's good now. Thank you very much, Ben, for your...
Okay. I respect that this lecture had some more obscure content in it, but it is state-of-the-art stuff. So you're now ready to begin correcting errors.
Officially baptized, I guess. So we have 10 minutes break. Please come back at 5 sharp because of the last session has to start on time due to IT support. Okay, so see you in 10 minutes.
Set down when you started.